Microporous crystalline materials such as zeolites and metal organic frameworks have potential applications for use as thin layers in membrane separations. Such microporous membrane materials have a potential for separating a wide variety of mixtures. To give just 5 examples of microporous membrane materials, let us look at DDR, that consists of cages of 278 cubic angstrom separated by 8-ring windows whose aperture is about 3.65 angstrom. ZIF 8 has cages of 1,168 cubic angstrom, and each cage is separated from adjacent cages by flexible 3.3 angstrom size windows. This dimension 3.3 is from the crystallographic information, and we will see later that in practice there is a high degree of flexibility, and guest molecules significantly larger than 3.3 can cross the window regions. Another type of microporous material is Hexiolite, Y zeolite. Both have the Faugesite or Fau topology. It consists of cages of 786 angstrom separated by 12 ring windows whose aperture is 7.2 angstrom. We could have one-dimensional hexagonal channels of MOF 74, where M could be magnesium, iron, cobalt, nickel, manganese. Or we could have a set of intersecting channels and use Mfr Zeolite. Mfr stands for mobile 5, and the channel dimensions is 5.5 angstrom, and this is a straight channel and it intersects the zigzag channel. These are the intersection sites. There are 4 intersection sites per unit cell of Mfr Zeolite. A wide variety of channel dimensions, window dimensions, cage dimensions are possible. And in this presentation, we focus on the important characteristics that determine the performance of a membrane, and that is the membrane permeance and the membrane selectivity. Ideally, we would like to have a combination of high permeance concomitant with high selectivity. However, normally the higher the selectivity, the lower the permeance, and there is usually a trade-off, and we will examine the various factors that determine the permeance and the factors that determine the selectivity of a membrane. One of the important things we would like to stress is that membranes in this category, consisting of narrow windows, have completely different characteristics than membranes that are constructed from materials that have larger channel dimensions or larger window dimensions. Before we go into details of the factors that determine the membrane permeance and the membrane selectivity, it is useful to define the various terms that we will be using in this presentation. We consider a microporous membrane layer of thickness delta. This layer could be a zeolite or a MOF. We consider ordered crystalline materials in this presentation. In other videos to come later, we will talk about polymer membranes and other types of membranes. We will not consider mixed matrix membranes today in our presentation. We consider the upstream compartment to have the partial fugacities F1 and F2 of components 1 and 2 that need to be separated. The upstream face of the membrane is considered to be in equilibrium with these partial fugacities, and the component loadings at the upstream face are Q1 and Q2, say typically in the units of molecules per unit cell or moles per kilogram. The partial fugacities of the components in the downstream compartment of the membrane are F1 sub delta, F2 delta. Usually these are significantly lower than the partial fugacities in the upstream compartment, and the corresponding loadings at the downstream face of the membranes Q1 delta and Q2 delta are lower than the loadings at the upstream face. And we have fluxes N1 and N2 across the membrane, and one of the components, say N1, permeates with a greater flux than component 2. In other words, the permeation selectivity is in favor of component 1. It is to be emphasized that these component loadings Q1 and Q2 need to be determined by applying the correct model to describe mixed adsorption equilibrium. In general, we need to use the ideal adsorbed solution theory, IAST, to determine the component loadings Q1 and Q2 for a given set of partial fugacities in the upstream compartment. Alternatively, in simple cases, we may apply the mixed gas Langmuir model. Most commonly, the partial fugacities may be identified with the component partial pressures, but I prefer to use a slightly more general term here, the partial fugacities. The component permeance is most commonly defined as the flux of that component divided by the driving force that is exerted on that component for it to transfer across the membrane. That driving force is the difference in the partial fugacities between the upstream and downstream compartments, that is F1 minus F1 delta, or delta F for that component. The component permeability is defined as the flux divided by the driving force divided by the membrane thickness, delta. So there is a factor delta that needs to be multiplied to the component permeance to obtain the component permeability. In experimental studies, if the precise thickness of the membrane is not easily determinable, it is common practice to use the component permeance. In case the component, the membrane thickness can be determined relatively accurately, we can determine the component permeability using the membrane thickness. We will see later that if we use molecular dynamic simulations, then the diffusivities in the membrane are easily accessible, and it is more convenient to determine the component permeability from MD simulations. The permeation selectivity is defined as the ratio of the component permeances, or it may be defined as the ratio of the component permeabilities. It is easy to derive a simple expression for the permeation selectivity. It's a product of the adsorption selectivity. The adsorption selectivity is simply the ratio of the component loadings divided by the ratio of the partial fugacities. That is S adsorption. S diffusion, the diffusion selectivity is the ratio of the diffusivity of component 1 to the diffusivity of component 2. To set the scene for this presentation, let us examine the separation of mixtures of carbon dioxide and methane using a wide variety of microporous zeolites and MOFs for the separation task. We used molecular simulations of adsorption and diffusion to determine the CO2 methane adsorption selectivity and CO2 methane diffusion selectivity for a 50-50 mixture of CO2 and methane at a temperature of 300 degree Kelvin. For a total upstream fugacity of 1 megapascal, we plot here the diffusion selectivity in the y-axis as a function of the adsorption selectivity. It is immediately clear that there are two classes of materials. The materials that are colored in blue have diffusion selectivities larger than unity, and also adsorption selectivities larger than unity, which is desirable because adsorption and diffusion go hand in hand. However, for the materials marked in black that include Hexiolite, NaY zeolite, magnesium MOF74, mordanite, copper BTC, zinc MOF74, Mfr Zeolite, MOF177, MTW, GME, LTL, you name it. There are several others. This is a different class of material where the diffusion selectivity is lower than unity, but the adsorption selectivity is larger than unity. So adsorption and diffusion do not proceed hand in hand. First thing to appreciate is that these materials are all cage window structures with window dimensions smaller than about 4.1 or 4.2 angstrom. These are colored blue. They are Chabazite, Lindertop A, LTA zeolite, TSC zeolite, that is the largest, zeolite with the largest cage volume, ITQ 29, ERI zeolite, ZIF 8. If we examine the differences between the blue and the black materials by looking at the characteristic dimensions, we note that all the blue materials have characteristic dimensions smaller than about 4 that correspond to the window dimensions, whereas all the other materials have characteristic dimensions larger than about 5 or 4.8 angstroms. Say the largest one is magnesium MOF 74 that has channels of 11 angstrom in size. Copper BTC, IRMOF 1 are large open structures that have large pore dimensions. MFI, typically 5.5 angstrom is here. I'll plot here the pore volume. So these are large open structures. So we see here that the high diffusion selectivity and high adsorption selectivity are possible with the blue structures, but they have low characteristic dimensions, and therefore, even though the diffusion selectivity is large, the permeance or permeability of carbon dioxide can be expected to be significantly lower than the black materials. So there is a trade-off. But purely on the basis of adsorption and diffusion selectivities, this class of materials, cage window structures with window apertures smaller than about 4 angstrom, are to be preferred. We examine in detail the class of materials that consist of cages separated by narrow windows with window apertures smaller than about 4.2 angstrom. These materials could be DDR, LTA zeolite, Chabazite, TSC, ZIF 8. This slide compares the window dimensions for cage type zeolites. We will see later that the minimum size of the window aperture in each case is relevant when comparing the diffusivities of guest molecules inside these structures. We should therefore expect that the diffusivities in DDR, which has the narrowest dimension of 3.65, to be lower than the diffusivity of the same guest molecule in Chabazite, and the diffusivity of that guest molecule would be larger in, say, LTA all silica zeolite. Small differences in the window aperture will make a large difference in the values of the diffusivities, and these differences could be about 1 to 2 orders of magnitude. This slide shows the intercage hopping of methane in ITQ 29, LTA all silica, and DDR. Let's look at the animations, and you can see clearly in ITQ29 the intercage hopping of methane molecules. Here, 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 here you can see this is for LTA. You can also observe the intercage hopping of methane. Here, here it has crossed the cage. The window dimensions of these two zeolites are larger than for DDR, and for DDR the diffusivity of methane is considerably lower than that for LTA and ITQ, and that is evidenced by the fact that most of the hopping occurs within the cage. And in this case, we track the trajectory of one methane molecule, and the trajectory is indicated by these blue lines. And up to this time, the methane molecule has not crossed the windows to any of the adjacent cages. And if we watch this window patiently, we will see one hop occurring to this window. Let's wait. Note that we are just tracking one methane molecule that was initially located here, and now it has entered this cage because the trajectory has entered the adjacent cage. So this intercage hopping occurs much less frequently than in these two types of zeolites. This slide summarizes the molecular dynamic simulation data for the self-diffusivities of methane in different cage type zeolites. The hierarchy of the diffusivities is dictated by the size of the window aperture. In each case, we use the d-min, which is the minimum dimension of the window aperture, to characterize the window size of that particular zeolite. For example, the red circles show the self-diffusivity data for LTA all-silica zeolite, which has a d-min value of 4.1 angstrom, and the inverted pink triangles show the self-diffusivity data for DDR, whose value of d-min is 3.65 angstrom. Note that the differences in the diffusivity values are about 2 orders of magnitude between LTA and DDR. Now, the diffusivity values are also a function of the concentration of the methane guest molecules inside the pores, expressed in kilomoles per cubic meter. For a comparison of the diffusivity values, we take the diffusivities at a loading of 1 kilomole per cubic meter, and that diffusivity values for these cage type zeolites is plotted as a function of the window dimension d-min, and we see that the self-diffusivity values at this loading correlates with d-min value. ranging from 3.65 to 4.1 angstrom, and the variation is about 2 orders of magnitude. So by appropriate choice of the cage type zeolite, we can manipulate the selectivity values for mixture diffusion. Let's examine the intercage hopping of carbon dioxide in DDR zeolite. Carbon dioxide is a pencil-shaped molecule, and the minimum cross-sectional dimension is 3.1 angstrom, and the only way CO2 can hop across the DDR window is in a lengthwise direction. So we will see animations of the intercage hopping of CO2 in DDR. And before we do that, let me say that we are going to track the trajectory of one of these CO2 molecules as it hops or attempts to hop from cage to cage. Let's start the animation. At the moment, it has only hopped within the cage, and there it has crossed the window and has approached and entered this cage, as you can see from the trajectories. It's attempting to cross this window, but it has returned to this cage. And now it's that same molecule is trying to cross this window and has not been successful so far and has returned to this cage. Then the net result is that the CO2 molecule that was tracked started in this cage, entered this cage, and spent all its time trying to hop to this cage unsuccessfully, and the attempt to hop across the window to this cage was also unsuccessful, and all the trajectories for CO2 are to be found within this cage. So for the duration in which that CO2 molecule was tracked, it underwent intercage hopping successfully only once. Let's examine Co2 Ch4 Mixture Diffusion in case type zeolites, chabazite, DDR, and LTA. Let's first have a look at the animations for chabazite. The CO2 molecule is attempting to enter this cage, but is hovering around the window site. This is for DDR. You can see the preferential perching of CO2 at the window regions. It stays at the window regions for a considerable amount of time before entering either of the adjacent cages. Intercage hopping of CO2 is much easier in LTA zeolite because the window dimensions are larger. Here you can see a CO2 molecule hovering around the window site. Molecular dynamics simulations for the diffusion selectivities for Co2 Ch4 mixtures are plotted here as a function of the total pore concentration expressed in kilomoles per cubic meter. The diffusion selectivities for each of these 4 cage-type zeolites decreases with increasing pore concentrations. The hierarchy of diffusion selectivities is dictated by the window apertures. DDR has the highest value for CO2 Ch4 selectivities because it has the smallest aperture size of 3.65 angstrom. The red circles show the selectivity values for all silica LTA, and these values are the lowest because the window dimensions of 4.1 angstrom in this case is significantly larger than the minimum dimension of 3.65 for DDR. For a pore concentration of 15 kilomole per cubic meter, the diffusion selectivity values are plotted against the window dimension d min, and we can see a reasonable correlation between the diffusion selectivities and the window dimensions for these 4 cage-type zeolites. The selectivity for DDR is about 1 order of magnitude larger than for all silica LTA zeolite. The company called NGK Insulators in Japan offer membrane modules which have a monolithic structure, and the inner walls of the tubes are coated with a thin layer, typically about 20 micrometers in size, this layer. And this layer consists of DDR zeolite that allows selective CO2 permeation from a CO2 methane mixture. In industrial practice, LTA all silica version is not used. Rather, we have cation exchange 4A and 5A zeolites that are commonly used. For 4A zeolite, we have 96 sodium cations per unit cell, and the location of these cations are shown by the blue spheres. Particularly noteworthy is the sodium cations partially block the windows, and therefore the diffusivities of the gas molecules are significantly lowered due to the hindering caused by the presence of cations at the window sites. In 5A zeolite, we have 32 sodium cations per unit cell and 32 calcium cations per unit cell. The locations of the sodium cations are shown by the blue spheres, and the location of the calcium cations are shown by the red spheres. In this case, none of the cations is to be found in the window regions, and therefore there is no hindering of the intercage hopping of gas molecules. Let us gain a qualitative understanding of the influence of extra framework cations on the intercage hopping of methane molecules. We look at both 4A and 5A. Here are animations prepared on the basis of MD simulations. The blue spheres are the extra framework sodium cations, and the green spheres are methane molecules. These are the window regions. These are the window regions, and we see that the window regions are occupied by the extra framework cations that appear to hinder the intercage transport of methane. If we look at LTA 5A zeolite, we see no cations in the window regions. The cations either blue or red spheres, and the green spheres of the methane molecules are able to enter the cage and cross it. Let's see how a microporous membrane is constructed. Take the example of a ZIF8. It consists of cages of 13 angstrom in diameter, and each cage is separated from adjacent cages by narrow 3.3 angstrom windows. These windows are flexible, and this flexibility allows molecules that are slightly larger than 3.3 angstrom to pass through these windows. Typically, the membrane would be constructed of thin layers of about 50 microns on a support, which is a macroporous. In this case, say a titanium support. And ZIF8 is a good choice for separation of mixtures of, say, carbon dioxide, methane, carbon dioxide, hydrogen, methane, hydrogen. And the important advantage of ZIF8 for CO2 methane separation is both adsorption and diffusion complement each other, leading to high permeation selectivities in favor of carbon dioxide. Even though the crystallographic data of ZIF8 indicates a window dimension of 3.3 angstrom, it is important to emphasize that the windows have a high degree of flexibility. This is demonstrated by MD simulations of the framework. We're going to look at the window along this direction. we can see the window structure appears to open and shut in a periodic manner, and this allows molecules that are larger than 3.3 angstrom to cross the window regions. We now move on to discuss the permeation characteristics of materials with more open structures with characteristic dimensions that are larger than about 5 angstroms. They could be, for example, MOF 74 with 11 angstrom hexagonal channels, Faugesite type zeolites with 12 ring windows that separate cages of 786 cubic angstrom, Mobile 5 zeolite with straight channels and zigzag channels of 5.5 angstrom in size, could be MIL 47, MIL 125, and other materials such as copper BTC, MOF 177, etc. Let us begin our discussions on the permeation characteristics of open structures such as nickel MOF 74, MFI, Faugesite, copper BTC. We start by examining the data on component permeances across a nickel MOF 74 membrane as reported by Lee in this paper. Plotted as a function of the kinetic diameter, we note that the component permeances do not correlate with the kinetic diameter, and the component permeance for CO2 is significantly lower than that of methane that has a higher kinetic diameter. In order to understand this experimental data, we look at MD data on the diffusivities of these gas molecules, plotted as a function of the isostatic heat of adsorption, that is a measure of the binding strength of the gas molecules. We note that the diffusivities correlate very nicely with the binding strengths. In other words, the stronger the binding, the lower is the mobility. Put more simply, sticky gases have lower mobility. This is going to be a recurring theme in the slides that follow. Let's move to diffusivities in Mfr Zeolite that consists of intersecting channels of 5.5 angstrom in size. The MD data on the diffusivities are plotted here on the y-axis as a function of the kinetic diameter. As for nickel MOF 74, shown on the previous slide, we note that the diffusivity of CO2 is much lower than the diffusivity of CH4, even though the kinetic diameter of CO2 is significantly lower. And the explanation is precisely the same. The diffusivities correlate with the binding strengths. In other words, sticky gases have lower mobilities, and the conclusions by combining the information for MFI zeolite with that of nickel MOF 74 is that the use of the kinetic diameter to correlate permeances is meaningless, even though almost every paper on membrane performance has plots of permeance versus kinetic diameter. Let's have a look at the structural topology of our zeolites. These consist of cages of approximately 11.5 angstrom. Each cage is separated from adjacent cages by 12 ring windows that have apertures which are approximately 7.2 angstrom. Let us examine the key properties such as polarizability, dipole moment, and quadrupole moments of gas molecules such as carbon dioxide, methane, carbon monoxide, nitrogen, and oxygen. Here I plot the polarizability versus the quadrupole moment, and we note that the polarizability of methane is practically the same as that for carbon dioxide, but carbon dioxide has a significantly higher quadrupole moment. We also note that the quadrupole moment of nitrogen is about a factor 4 higher than that of oxygen. Of these gas molecules, only carbon monoxide has a dipole moment. For separating CO2 from methane, we can exploit the large difference in the quadrupole moments between CO2 and methane. Methane has a 0 quadrupole moment by electrostatic interactions with the extra framework cations. Similarly, the selective adsorption of nitrogen from mixtures with oxygen is achieved because of the large quadrupole moment of nitrogen that is 4 times larger than that of oxygen. For CO2 capture from flue gases, we rely on the large differences between the quadrupole moments of CO2 and nitrogen. And also the polarizability of CO2 is higher than that of nitrogen. Let us examine the electrostatic interactions between a gas molecule and the extra framework cation. That can be either lithium, sodium, potassium, magnesium, calcium, strontium, or barium. Also indicate here the size of the cation, the radius of the cation in angstrom values. Let R represents the distance between the center of the gas molecule and the center of the cation. Basically, we can distinguish between 3 types of electrostatic interaction potentials. One due to induced dipoles. The second one due to the interaction of the electrical field with the permanent dipole of the guest molecule. And thirdly, we have the interaction of the electrical field gradient with the quadrupole moment of the gas molecule. Here Q represents the charges of the extra framework cation, and R is the distance from center to center between the guest and the cations. In all cases, we note that the potential energy of interaction is proportional to the charge, or the square of the charge, and inversely proportional to the distance to the power 2, distance to the power 3, and the center to center distance to the power 4. In other words, larger electrostatic interactions are achieved with smaller cations because the center to center distance is smaller if the radius of the extra framework cations is smaller. The electrostatic interactions increase with the valency of the extra framework cation. A bivalent barium cation would contribute to a greater extent to the electrostatic interactions. And larger dipole, larger quadrupole, higher polarizability will all lead to larger magnitudes of electrostatic potentials. In this slide, I would like to demonstrate the anti-synergy between the adsorption strength and the mobility of a gas molecule. And as an example, let's take carbon dioxide. The binding strength or the binding energy is reflected in the isosteric heat of adsorption, and the mobility can be quantified by the self-diffusivity of CO2. Both these parameters, the isosteric heat of adsorption and the self-diffusivities, are plotted as a function of the surface potential that serves as a proxy for the spreading pressure. The reason for the choice of the surface potential as x-axis is clearly explained in my presentation on the spreading pressure that is available on my YouTube channel. With increasing number of extra framework cations, as we move from all silica faugicite to NaY zeolite with a silicon to aluminum ratio of 2.55 to NaX zeolite with a silicon to aluminum ratio of 1.23, we note that there is a significant increase in the isosteric heat of adsorption. In other words, the strength of binding increases with the number of extra framework cations, in this case sodium. This is to be expected because of the large quadrupole moment of CO2. However, stronger binding implies lower mobility, and we note from the plot of the self-diffusivity versus the surface potential that the mobilities decrease with increasing number of extra framework cations. As we move from all silica faugicite to sodium Y to sodium X. So the takeaway message from this slide is that the stickier the molecule, the lower is its mobility. Cation exchange faugicite zeolites also find use in membrane constructs in which a thin layer, typically 50 micrometers of the zeolite, is used as a Perm selective device to separate gaseous mixtures. The permeation selectivity is a product of the diffusion selectivity and the adsorption selectivity. Let's look at the relative values of the adsorption selectivity and diffusion selectivity for all silica faugicite, for sodium Y and sodium X. With increasing amounts of extra framework sodium cations, the adsorption selectivity of CO2 with respect to methane increases by about 2 orders of magnitude in going from all silica to NaX that contains 86 aluminum atoms per unit cell. However, the increase in the adsorption selectivity is at the expense of diffusion selectivity, and NaX zeolite has a diffusion selectivity of CO2 with respect to methane that is about 1 order of magnitude lower than that of all silica fungicide. The decrease in the diffusion selectivity is due to the fact that CO2 is much more strongly adsorbed, is much less mobile than methane. The net result for use in membrane constructs is that while adsorption selectivity increases with increasing number of extra framework cations, the diffusion selectivity decreases, and the permeation properties of the membrane is a reflection of the anti-synergy between adsorption and diffusion. Let us see how that plays out. Consider the permeation of 50-50 feed mixtures of CO2 and methane at a temperature of 300 degree Kelvin and a total fugacity of 1 megapascals. This is a Robson plot of the CO2 methane permeation selectivity plotted against the CO2 permeability. The best performance of any membrane is in the top right-hand corner. We would like a performance that is right at the top right-hand side of the Robson plot. This line represents the Robson upper bound, and I present here the data for NaX, NaY, and all silica fungicide. These data are calculated on the basis of a combination of molecular simulations of mixture adsorption and MD simulations for mixture diffusion. We note that by increasing the number of extra framework cations, the permeation selectivity increases, and therefore increasing the number of cations is a beneficial thing from a permeation selectivity viewpoint. However, we note that the permeability, which is related to the mobility within the membrane, is reduced by about 1.5 orders of magnitude in going from fungicide to NaY to NaX. And therefore, there is a trade-off between permeability and permeation selectivity in choosing the right silicon-aluminum ratio to be used in membrane constructs. The important finding that has emerged in the discussions on diffusion in more open structures is that stickier guests have lower mobility. There is a further effect that needs to be considered in membrane permeation of mixtures of sticky and less sticky molecules. The sticky molecule that is tardier or more slow moving will have the effect of lowering the mobility of the non-sticky, more mobile components, as illustrated in this familiar traffic scene in India. These slow-moving elephants have the effect of slowing down the molecular traffic or vehicular traffic of the more mobile motor cars in this channel. We will show that this slowing down effect manifests itself in all such open structures such as Mfr Zeolite, Faugesite, nickel MOF 74, etc. We begin discussions on slowing down effects by looking at CO2 hydrogen diffusion in Mfr Zeolite. Let's look at permeation of mixtures of CO2 and hydrogen across an Mfr membrane. The experimental data plotted here are from Sundström from Journal of Membrane Science. They have measured unary permeances of hydrogen, shown by these diamond symbols, unary permeance of CO2, shown by the open circles, permeances of CO2 hydrogen mixtures, shown by the fill symbols. The red circles are for CO2 permeance in mixtures of CO2 and hydrogen. The yellow diamonds are hydrogen permeances in the CO2 hydrogen mixtures. We note that the permeance of hydrogen in the mixture is about 1.5 to 2 orders of magnitude lower than the unary permeance. On the other hand, the permeance of CO2 in the mixture is only slightly lower than the pure component permeance when the component permeances are plotted against the upstream partial pressures Pi0. The mixture permeation experiments were performed with equal partial pressures of CO2 and hydrogen in the upstream compartment. We examine the reason why the permeance of the hydrogen in the mixture is so much lower than the unary permeance of hydrogen. Let us gain a qualitative understanding how the strongly absorbed CO2 influences the mobility of hydrogen molecules within the intersecting channel structure of Mfr Zeolite. Let's have a look at the animations. The gray spheres are hydrogen molecules, and we can see that it hops around the channels very fast, but somewhere down the line it has to cross a CO2 molecule, but the CO2 molecule just refuses to vacate its absorption site, and therefore hydrogen cannot bypass the CO2 molecule. In other words, the mobility of hydrogen is reduced due to the presence of strongly absorbed CO2. Here I use the analogy with a checkerboard to explain the slowing down effects that hydrogen experiences in mixtures with CO2 within the intersecting channels of Mfr Zeolite. Here's the checkerboard where each of these squares represents an absorption site within Mfr Zeolite. The red circles are CO2 molecules that are strongly absorbed, and therefore each of these red circles vacates or hops to another adjoining site at a frequency that is much lower than the frequency with which hydrogen, the smaller molecule, jumps from one site to an adjacent site and traverses the intersecting channels of MFI. I draw here a contour that the more mobile hydrogen can occupy, but to go beyond that contour, CO2 has to vacate that adsorption site. So it is akin to a game of musical chairs. For hydrogen to occupy a chair, that chair has to be first vacated by the tardier, more strongly adsorbed CO2. Put another way, the mobility of hydrogen is correlated with the mobility of the tardier partner CO2. And the net result is a slowing down of hydrogen in mixtures containing CO2. For Co2 Ch4 mixture diffusion in Mfr Zeolite, the mobility of methane is severely reduced due to the more tardy CO2 that has a stronger adsorption strength. We can have a look at the animation to illustrate that. We can see that the CO2 molecule refuses to budge from the intersection sites, and therefore preventing the methane molecules to travel very far along the channels. Let's examine mixtures of methane and ethane within the MFI channels. The mobility of methane is reduced due to the more strongly adsorbed ethane molecule that vacates the adsorption sites less frequently and therefore slows down the mobility of methane. The same is true for mixtures of propane and methane. Propane molecule is ensconced at the intersection sites and prevents the methane molecule from going past it. So the mobility of methane is reduced by the presence of propane in the mixture. We now turn our attention to a different class of slowing down effects that is caused by preferential location of certain types of molecules at the channel intersections of Mfr Zeolite, such as aromatics and branched alkanes. Let's look at benzene. Benzene prefers to locate at the intersections, and it rotates around the intersections and can move along the channels, but its diffusivity along the channels is rather low. The same is true for cyclohexane, shown on the right. Also prefers to locate at the channel intersections, and its motion along the channels is rather restricted. So the preferential location of these aromatics, benzene or cyclic compounds, cyclohexane, at the channel intersections leads to slowing down due to intersection blocking. If the intersections are blocked, the entire traffic along this channel and this channel is brought to a complete standstill. Let's have a look at a mixture of benzene and methane. Methane has a higher mobility, but the path it follows is restricted due to the fact that the benzene molecule is blocking the intersection sites. This is experimental data on the self-diffusivity of methane with increased loading of benzene. The self-diffusivity of methane is reduced by about 2 orders of magnitude when the loading of benzene corresponds to 2 molecules per unit cell. So the traffic comes to a virtual standstill if more than 2 intersection sites are occupied. The understanding and quantification of such traffic junction effects is of vital importance in the design of fixed bed adsorbers and fixed bed reactors, such as reactors for ethylation of benzene to produce ethylbenzene. Due to legroom considerations, branched alkanes such as isobutane, 2-methylpentane, 2,2-dimethylbutane prefer to locate at the channel intersections. Let's have a look at the animation. On the right-hand side, I show experimental data on the self-diffusivities of normal butane in a mixture of normal butane and isobutane at a total loading of 4 molecules per unit cell. And we note that the self-diffusivity of normal butane that can locate anywhere along the channels is reduced by about 2 to 3 orders of magnitude when the loading of isobutane is increased in value to more than 2 molecules per unit cell. So the intersections blocking has a severe influence on the mobility of normal butane along the channels. This is another example of how important intersections in Mfr Zeolite are to the maintenance of free-flowing traffic along the channels. If you block 2 intersections or more, the entire traffic is brought to a standstill. For water alcohol mixture diffusion in zeolites and MOFs, there is hydrogen bonding between water and alcohol and between alcohol and alcohol. And this clustering due to hydrogen bonding causes mutual slowing down. The mobility of both partners in the mixture are reduced due to clustering phenomena. Some indication of clustering is also evident for these animations which show clustering of methanol and ethanol mixtures within the cages of Mfr Zeolite. In this presentation, I have made a distinction between two classes of materials. Firstly, we have cage window structures in which the window dimensions are less than 4.2 angstrom. In this case, an important parameter that dictates the permeation properties is the minimum dimension of the pore of the window opening. Small differences between the window aperture leads to differences in diffusivities by about 2 orders of magnitude. And this can be exploited to obtain high permeation selectivities. Another point that was emphasized is that pencil-like molecules such as carbon dioxide, nitrogen jump lengthwise across the channels, and it is pointless to talk in concepts of the kinetic diameter. Moving on to the second class of materials, in which we have window or channel dimensions larger than about 5 angstrom. Here again, we have emphasized that the concept of the kinetic diameter to correlate component permeances is irrelevant or not applicable, because the permeance in such structures is dictated by the stickiness or the binding strength of the molecule. Sticky molecules have lower mobility. This influences the permeation selectivity and the diffusion selectivity. There is also further effect that has been highlighted, and that is due to the correlations between the jumps of molecules. A CO2 molecule that is stickier reduces the mobility of more mobile partners. We've also highlighted for Mfr Zeolite the concept of intersection blocking. If the intersections are blocked, then the whole traffic can be brought to a standstill. And finally, we have also mentioned the mutual slowing down due to hydrogen bonding between molecules.